Let's look at another example of a tangent plane problem. In this example, we look at the following problem. That is to determine points on the ellipsoid, x squared plus 2y squared plus z squared equals 28, where the tangent plane is perpendicular to the line with parametric equations x equal 5 minus 10t, y equals 3 plus 4t, and z equals 4 minus 2t. Well, this again involves understanding the geometry of vector analysis. So if we need a plane that is perpendicular to this line, then certainly we would like to know that the normal to the surface would be parallel to this line. That would give us the geometry that we need. So now if we look at this, we can write down the actual direction of the line by just looking at the coefficients of the parameter t. So we have a -10, we have a 4, and we have a -2. Now, of course, we can preserve the direction if we go ahead and factor some of the extra in here. We don't need extra numbers, certainly. So let's go ahead and factor a -2. So this will leave us a 5, a -2, and a 1. So basically we have a vector now that we can utilize here in our computations, but that'll be the next step. So, or a later step. So now what we want to do is look at the surface normal. So we will write an implicit equation. So we have F equals, in this case, x squared plus 2y squared plus z squared minus 28. So here is our implicit equation. So we need to look at the gradient. So let's look at the fx, or the x partial. And this will just give us a 2x. Very simple. The y partial will just be a 4y. And the z partial is just 2z. So this implies, if you will, we have a gradient or a surface normal with the following coordinates. We have 2x, 4y, 2z. And now, of course, we can get rid of the extra, so to speak. The 2 can be factored, x, 2y, and z. So as I was talking about before, the geometry will be satisfied as long as the gradient, in this particular case, is parallel to the direction of the line here, given parametrically. So this would imply, so we'll just say for parallel vectors, we have, and we can just focus on, again, the vectors extraneous to the scalar factors. So we have x, 2y, z equals, and for some constant alpha, and in this case, we'll equate this to 5, -2, 1. Now we can just run this inside. So this will give us, so we can do some equating. We have what, 5 alpha, -2 alpha, and we have alpha. So equivalently, x equals 5 alpha, 2y equals -2 alpha, and z equals alpha. Now, of course, here we can absorb the 2, so y equals negative alpha. So this gives us a prescription of what the coordinates x, y, and z should be relative to alpha. So now we can use the original equation to figure out what alpha is. So now substituting, we have, again, 25 alpha squared plus 2 times a negative alpha squared plus alpha squared equals 28. So we're just substituting into the original equation here. And then, of course, we have alpha squared in all of the terms here. So we have alpha squared, 25, so the arithmetic is real simple, plus 2, plus 1, but that's alpha squared times a 28 equal to a 28. So clearly, the 28's absorbed. So we're left with a very simple equation, alpha squared equals 1. So by square root principle, alpha is plus or minus 1. So these values of alpha will give us the parallel condition that we need. So for instance, for alpha equals 1, we simply go to our coordinates. We have 5, negative 1, 1, just following the coordinates here. And then for alpha equal negative 1, the coordinates will now be negative 5, positive 1, and a negative 1. So this would give us the points where the actual tangent plane is perpendicular here to the given line. That is points 5, negative 1, 1, and point negative 5, 1, negative 1. And we are done.